Case 3 and case 4 work very similarly to case 1 and case 2, except now we're going to deal with the possibility that some of the factors are irreducible quadratics. Case 3. Unrepeated irreducible quadratics. If we have irreducible quadratics, then the partial fractions that correspond to them don't have constants on top, they have linear terms on top. So if q of x is equal to ax squared plus bx plus c for an irreducible quadratic, and then maybe linear terms, the partial fraction that corresponds to the ax squared plus bx plus c looks like this. So what corresponds to the irreducible quadratic is this piece. If I have a denominator that factors into a piece that can't be reduced, then the partial fraction that goes with it has this ax plus b on top. Linear terms that are in here still correspond to linear single partial fractions like this. So let me show you what that looks like in a breakdown. Suppose that we looked at the integral of x plus 2 over x plus 1 times x squared plus 1. So that's a product in the denominator of a linear term and an irreducible quadratic. You can tell that it's irreducible because b squared minus 4ac is negative 4. So I have to use a partial fraction here. And the general rule is if you see a rational function, it's almost certainly going to be a partial fraction problem. So the partial fraction step looks like this. Corresponding to the linear term in the denominator is a partial fraction of our usual form. Corresponding to the quadratic term in the denominator, we get this linear piece in the top over the irreducible quadratic. So linear terms go with linear partial fractions. Irreducible quadratics go with irreducible quadratics in the denominator that have lines in the top. The process of finding the a, b, and c is the same as before. So we're going to multiply through by the denominator. And if we do, what we're going to get is x plus 2 is equal to a times x squared plus 1 because of cancellation, plus bx plus c times x plus 1. Now we can multiply this out and collect like terms just like usual. There actually turns out to be a faster way to calculate a, b, and c that I'd like to point out here that can reduce the amount of work that you have to do. So I could make this equation easier if I could find numbers I could plug into it that turn certain terms into zeros. So for example, if x was equal to -1, what would this equation turn into? The reason I choose x is equal to -1 is because that makes this term into nothing. And 0 times anything is 0. So this would turn into the equation -1 plus 2 is equal to a times -1 squared plus 1 plus, who cares what this is because it's multiplied by 0, and you end up with the equation 1 is equal to a times 2. And so a must be a half. So before we've even got started with the system of equations, I can always pick off the coefficients that are affiliated with linear terms by finding things that zero the equation out and preserve certain coefficients that I get simpler equations for. That's actually worked on all the problems that we've done so far. If we were going to be consistent about the way we've been doing this, we'll do this with the system approach. So x plus 2 is equal to ax squared plus a plus, okay, so we get a bx squared, and we get a bx, and we get a cx, and we get a c. Now I'm going to collect like terms so I can do my comparison. X plus 2 is equal to a plus b x squared. And then I have a bx and a cx. And I have an a and a c for my constant. So when I build my system of equations, I compare like terms to like terms. The constant on this side is 2. The constant on this side is a plus c. So 2 must be equal to a plus c. The coefficient of the x term is b plus c. The coefficient of the x term is 1, so it must be the case that 1 is equal to b plus c. The coefficient of the x squared term on this side is 0, so 0 must be equal to a plus b. Now this is a nastier set of equations than we've dealt with so far because we have 3 equations and 3 unknowns. We have to be consistent about eliminating. So why don't we eliminate the c? So we can combine these 2 equations in a way that eliminates c, and that will give us an equation that has a's and b's that we can compare with the third equation. So I could subtract the second equation from the first, and that will give me the new equation. 2 minus 1 is 1. A minus b is a minus b, and c minus c is 0. So if I subtract the first from the second, I get this. The second equation is still, or we're going to use for our second equation, 0 is equal to a plus b. We just carry this over. If I add these together, I get 1 is equal to 2a, and so a is equal to 1/2. Of course, we already knew that a was equal to 1/2 because we did it the other way. But supposing that we were being consistent, this is how we would do it. If a is a half, then because a plus b is equal to 0, that's going to force b to be equal to minus a half. And since a plus c is supposed to equal to 2, then c must be 3/2. I get that just by taking these numbers and plugging them back into these equations to solve. So that means that our original problem looks like this. The integral of x plus 2 over x plus 1 times x squared plus 1 dx is really the integral of, let's see, we had a 1/2 over x plus 1 and a negative 1/2 x plus 3/2 over x squared plus 1. And I'm very close to being able to solve this problem now. I've got one more step to do, which is when I've got these quadratic denominators, typically what will happen with the lines is we'll have to split this up into 2 functions, one of which will be a u substitution, and the other one of which is going to be some kind of inverse trig substitution. In this case, we get the integral of 1/2 over x plus 1 plus negative 1/2 x over x squared plus 1 plus 3/2 over x squared plus 1 dx. This is a log, this is a u sub, and this is an arctangent. So from this point, you can use techniques that we've already done to write down what the final answer should be. Case 4 looks like case 2, except now we've got repeating irreducible quadratics. And so we have to deal with that as well. Case 4. For case 4, this is where q of x has irreducible quadratic terms that repeat. And here we've got the same sort of structure that we saw in the earlier examples of the rational functions. So, for example, if I have q of x has a term that looks like x squared plus 1 to the third times some linear pieces, then the partial fraction representation of f is going to have a irreducible quadratic fraction for the first copy of x squared plus 1 and another irreducible quadratic fraction for the second copy and another irreducible quadratic fraction for the third copy. It's easy to see that this starts getting out of control when you have lots and lots and lots of these going at the same time because the algebra gets too complicated. Fortunately, computers and modern algebra systems can let us solve for these things very easily. Let's do one final structural example where we don't find the coefficients, and just to show how we take a really complicated expression and write it down in a partial fraction decomposition. So let's suppose that you had something like f of x is equal to x squared plus x minus 2 over x plus 3 to the third times x squared plus 2 to the second times x plus 4. If I was trying to write down the partial fraction decomposition, it would look like this. A over x plus 3, because that's for the first linear term, plus b over x plus 3 squared plus c over x plus 3 to the third plus dx plus e over x squared plus 2. That's the first copy of the irreducible quadratic. Plus fx plus g over x squared plus 2 squared plus h over x plus 4. So this monstrosity is what this decomposes into. But as big and ugly as this is, it builds out into a linear system which can be solved with matrices or various other computer techniques. And unlike this function, this can all be integrated. Because I look at this and I say to myself, natural log, easy U substitution, some kind of inverse tangent, easy, this is an inverse trig function, and that's a log. Okay? So what did we learn? We learned that linear terms correspond to linear partial fractions. We learned that repeated terms correspond to repetition in the partial fractions. And we learned that irreducible quadratics correspond to quadratic partial fractions, and repeated irreducible quadratics correspond to repeated and increasing power in the irreducible quadratic partial fractions. Partial fractions can seem like sort of a slog. Usually the important part is in working in small examples where you can very quickly find the a and the b. There's various methods of doing that quickly. Or in larger examples where you provide these bits and the computer tells you what the a through b, c, d, e, f, and g are. Practice your examples. And part of what I want you to practice is picking out when you know to use which type of integration. All right, I'll see you for the example video.